You need to put on the headphones. Welcome everyone to the Cryosphere Pavilion. For those of you who are here in person, you will need to put your headphones on. I'm looking for a sign that, okay, so I'm coming through. This is a very noisy and hot environment, and we're really appreciative of those of you who are here in person today. It's our real pleasure to host this event of the Clean Arctic Alliance, of which my organization, the International Cryosphere Climate Initiative, is a part. The purpose, of course, is to combat pollution from shipping in the Arctic. In particular, black carbon is going to be a focus of this event. So without further ado, and we apologize that we're starting late. I'll be turning this over to the moderator for this event, Ms. Nancy Garcia, who is from this region.
Thank you very much, everyone. Thank you for being here. And for those of you who are online, thank you for joining us. I want to thank the International Cryosphere Climate Initiative for the opportunity to host and participate in this event, Super Pollutants, Arctic Shipping, Myths and Realities. So since we have a lot of speakers, I'm going to turn the microphone to our first speaker, James Kirkman. James is a glaciologist and climate scientist. He currently serves as the Chief Science Advisor and Coordinator of the Ambition on Melting Ice, a high-level group on sea level rise and mountain water resources, a 25-country group founded at COP27 that aims to raise the urgency of emissions reductions to prevent growing and irreversible global impacts from cryosphere loss. James has previously worked as a geologist with the British Antarctic Survey and as a snow scientist at the International Center for Integrated Mountain Development in Nepal. He received his PhD and Master of Philosophy degrees in Antarctic Climate Science from the University of Cambridge and has a BSc in Geography from Durham University. So thank you very much, James, for being here.
Thank you very much, Nancy, and I hope this is coming through okay. So, thank you all, both who are attending this online and also here in an extremely warm and humid conditions in Belém today for COP30. My name is James Kirkham, as I was just introduced, and for this session I was asked to give a brief scientific overview of the Arctic climate crisis. But as you can already see on these slides, sometimes data speaks a lot louder than words, and these temperature data over the last 4 decades or so really give us an indication of the danger that we're currently in the Arctic climate crisis. So we're all here at COP30 and we're negotiating, but it's a decade from the Paris Agreement, and yet we still cannot negotiate with the melting point of ice. All of these headlines are just a fraction of the news that has been generated by changes to the Earth's polar regions in just the last 12 months, and little of it is good. Ice losses are accelerating, climate and weather extremes are being supercharged by climate heating, knock-on effects on ecosystems and the rest of the planet. Now, the reason that so many of these impacts in the Arctic are obvious already today is that the polar regions are warming much faster than the global average. So what you can see here is global average temperatures have warmed already by about 1.3 degrees compared to pre-industrial overall. But if we compare that to the Arctic, you can see that the Arctic has warmed by nearly 4 times the global rate. And what this means is that we're now heating the Arctic cryosphere with temperatures that are 2 or 3 degrees warmer than they were in the 1980s. Now, last year in the Arctic was the second warmest year on record and the wettest year on record. The last 9 years have been the warmest on record. And in particular, as you see this getting worse and worse over time, with anomalies getting larger and larger, I want to highlight last month, in particular October, which temperatures were really off the charts. Now, all of this continual rise in temperatures and growing extremes are having a visible effect on the Arctic cryosphere, including on the globally important reserves of sea ice, which hold really the dial to the Earth's thermostat. Now, in the last 40 years alone, let me change the slide. Excuse me, the slide is taking a while to change. In the last 40 years alone, the Arctic has lost about 2/3 of its volume of polar sea ice, and a particularly sharp decline occurred around 2007, which you'll see once this video begins to play. Here you go. So in the bottom left here, you've got the original frame in 1984, and the colours mark the age of the sea ice, with younger ice being greys, about 0 to 1 year old, and this really old, dense white sea ice is declining over time. And you'll see as we come to 2007 here that we shift into an abrupt shift in sea ice, so that basically there's not really any old sea ice left in the Arctic Ocean today. And the result of that is that we're left with a different regime which is much younger and thinner, and because of that more mobile. And that means that although sea ice extent is declining in the Arctic, it's more mobile, which is actually more hazardous to shipping. Now, the overall effect of these quite dramatic declines in sea ice is that its planetary cooling effects, the dial of the Earth's thermostat, has now reduced by about 14% since the 1980s. And this will enhance summer ocean heat uptake, or amplify warming in these regions even further, and contribute more and more to extreme weather. Now, elsewhere, ocean acidity has reached really critical levels, and science published this year has highlighted this, especially for the Arctic and the North Atlantic. And as you can see here, science has now shown that, especially in the Arctic Ocean, we've now crossed a planetary boundary for ocean acidification. And this will reduce habitats for keystone shell building species that are vital to the components, really, the building blocks of those marine food webs. So what about the future? So we're here, and pre-industrial on this graph is in grey, and really the outlook for the Arctic is, even if temperatures can be kept at 1.5 degrees, the Arctic is still going to experience a radical shift in conditions over the coming years. And so, as you can see by this pink graph here, having a 1.5 degree world will result in extremely warm conditions compared to pre-industrial by about 300 days of the year. But that is really nothing compared to our current emissions pathway of 2.6 or 2.7 degrees by 2100, in which virtually every single day of the year in the Arctic will have temperatures extremely much higher than the pre-industrial temperatures. And particularly in the winter, the second row here, temperatures will be about 10 degrees warmer than pre-industrial. So what does this mean for the future of Arctic sea ice? Continuing with our current pledges that we're heading towards right now will essentially mean the Arctic Ocean will lose its permanent sea ice cover. Ice-free conditions in these will occur every single summer for every single year and will last for several months. So you see September here is virtually free of sea ice. The impact of this will be profound. It will be like putting a radiator next to the Greenland ice sheet. However, with ambitious mitigation, Arctic summer sea ice will maintain around the record low conditions experienced in 2012. And although we may see some ice-free summer conditions in the coming years, inevitably, even as soon as the 2030s, we can limit this and we can protect that really vital store and reflective ability of Arctic sea ice. Now, moving on to our polar ice sheets here, and these are undergoing extremely rapid change. So the colours show how much mass has been lost over the last 20 years or so. Red is bad in these animations here, and what you can see is that losses have quadrupled since the 1990s. Now, all of this sea level rise is having a really dramatic effect. And if someone could just advance the slide to me because it's not working. Because of these ice losses, sea levels are rising about twice as fast as they were 30 years ago. And what this is actually doing is, because of the amount of fossil fuel pollution we've already pumped out into the atmosphere, it's adding on and making the damage caused by extreme weather events we're experiencing all the time now. We've seen terrible damage recently in the hurricane season. Every single year it's getting worse and worse. And attribution scientists are now able to show that the sea level rise we've had to date is adding billions of dollars onto the cost of individual storms. Now, with that damage in mind, scientists are seriously worried because our ice sheets are vulnerable to a series of vicious amplifying cycles. And we'll just skip over this in terms of the slide, but as... Oh, hang on, please go back. No, back. Play. Okay, one more. Apologies for this pointer not working. There we go. So what you'll see here is the surface of the Greenland ice sheet here is actually lowering down. And this is a massively dangerous situation to be in, because as the ice in the red here gets lower and lower, the ice surface is lowering down into warmer air temperatures, which then of course causes more melting and more lowering. So it's this vicious amplifying cycle affecting the Greenland ice sheet. Now, prominent scientific findings published this year, if we can advance the next slide please, show that even our current temperatures of 1.2 degrees, if we stay there for long enough, is not going to be sufficient to limit damage from our ice sheets. And in this regard, 1.5 degrees that we're aiming towards, or even struggling to limit towards, overshoot in the next 5 years or so, is far too high as a long-term goal. And so to avoid damage from global ice sheets is we're going to require a global temperature probably cooler than present, maybe about 1 degree above pre-industrial. So really, we're here talking about 1.5 or even 2 degrees, but really, we should be talking about 1. Now, the final part of the article I want to touch on is permafrost. And what this does is once it thaws, the microbes in there begin to decompose the organic material in the soils and release that as emissions of methane and carbon dioxide. And what that does is, as that thaws, it reduces the amount of headroom we have left to meet these key climate targets, because it's reducing the amount of carbon budget that is remaining. Now, permafrost emissions, as you can see on the right-hand graph here, were included in the last IPCC assessment, but recent science is actually increasingly pointing out the process of abrupt thaw on the left here, which is a local scale tipping point in the landscape. And when you add these in to our there we go, comparison to IPCC, you see that basically the amount of gap we have left between meeting these key targets is getting smaller and smaller. Now, at least about 30% of the Arctic's land ecosystems are currently a net source of emissions, and these are going to become more and more and more as temperatures rise. It's often useful to compare the size of this to a country. We often talk about permafrost as the country of permafrost, because emissions today are already the size of those from the country of Japan, a top 20 emitter. But if we continue emitting, and even if we can limit warming to 1.5 degrees or 2 degrees, the permafrost extent will still shrink dramatically through to 2100, and that will release emissions every single year equivalent to those currently of India or the EU. So an enormous source of permafrost emissions to the atmosphere. But if we go continuing on our current pathway, which is going towards 3 degrees, we're going to see a dramatic reduction in permafrost extent across the Arctic. And this will be like having another China or another the US in the world emitting carbon dioxide and methane every single year. Now, as well as emissions, permafrost thaw threatens the homes, livelihoods, and cultural heritage of over 3 million people living in the Arctic. And a lot of this area will degrade and reduce their homes and these areas by 2050, so on really short timescales here. In Alaska alone, damage estimates for the coming decades go into the billions, so 37 to 51 billion, under a range of different emission scenarios. So I want to end with a statement really about what we're doing here at COP30. So the latest UN emissions gap report shows that countries are far off target to meeting the goals of the Paris Agreement, which will result in the Arctic experiencing some of the worst scenarios and projections of future change that I've just shown you in this presentation by the end of the century. But there is still hope. So new work presented last week by Climate Analytics and the Potsdam Institute showed that with action starting this year in 2025, we can still bring temperatures down to about 1.2 degrees by the end of this century. These pathways necessitate urgent action, emphasising phase out of coal in the 2040s, gas in the 2050s, and oil in the 2060s, alongside halting and reversing deforestation, cutting emissions of methane, black carbon, and other short-lived climate forces, and also scaling up land-based carbon dioxide removal. If we can do this, and it is still feasible to do this, we can reach net zero in the 2060s, 1.2 degrees or so by the end of the century, and then declining to 1 degree or below thereafter, which is the true safe planetary limit for the Earth's cryosphere, polar regions, and mountain glaciers. So with that, I will leave you and say thank you very much on the last slide, and apologies for the tech issues, but thank you for staying with me there. Thank you.
Thank you, James. Thank you for your presentation. Our next speaker is going to be Rolf Roven. He's from AMAP, and Rolf is the Executive Secretary of the Arctic Monitoring and Assessment Program. Roven holds a PhD in Northern Populations and Ecosystem and an MBA in Strategic Management and Economics from UiT, that is the Arctic University of Norway. He has authored several scientific articles on Arctic socio-ecological systems and environmental impacts. Thank you, Rolf.
Thank you, and good afternoon, everyone. I'm going to talk a bit about, try not to hear my own voice in my head. I'm going to talk about super pollutants in the Arctic and why they are important. So I'll take you a bit through it, including also how AMAP and the Arctic Council have been addressing those and brought them forward to the international science and policy arena from the very beginning. Okay, here we go. Just say, so the Arctic Monitoring Assessment Program was established in 1991 as part of the Arctic Environmental Protection Strategy. Sorry, I just came from the Nordic Pavilion where you had to almost eat the microphone. So we're trying to adjust here. So we were established in 1991 with a mandate to monitor and assess trends and levels of contaminants as well as climate change in the Arctic, how they affect ecosystems, as well as humans living in the Arctic, including human health, how climate and contaminants interact as multiple stresses, but also, in particular, to bring forward science-based, policy-relevant recommendations to policy processes. I'll skip this one. Okay, why is this? Okay, it seems like we're going to go all the way back. Could you press one more slide? One more slide? Okay, good. I think I'll just say next. Well, so what we do is we produce scientific reports, peer-reviewed scientific reports. However, you know that it's quite hard to have a policymaker read about 1,000 pages of science, so we condense them down to 20-page reports which is purely scientific summaries as well, in addition to policy recommendations which are negotiated. Our science is not negotiated. But also to have those data, we need to run the monitoring programs. So we are running several monitoring programs and guidelines to make sure that we harmonize the data we collect in Arctic. So we are sure that we bring forward actually effects and not just differences in the way we monitor things. Our results act as advice to the Arctic Council and what we call senior Arctic officials, but also more importantly, in some cases, to the international arena. We work closely with UN Environment, IPCC, the Stockholm Convention on Persistent Organic Pollutants, the Minamata Convention on mercury, and here the Air Convention on Air Pollution. Next slide, please. Yeah, so as you can see here, some of the organizations we work closely with, and in this case, both the long-range transport is important, as well as the Air Convention. Next slide, please. So, why is short-lived climate pollutants important in the Arctic? Well, James just said the Arctic is warming 3 to 4 times as fast as anywhere else in the world. There's no place in the world where change is happening so fast. Not only when it comes to surface temperatures, but oceans are acidifying 3 to 4 times as fast. Wildfires have quadrupled since 2010, and permafrost is thawing rapidly. But what I really like to show is this graph, what you see here. You see the temperature range on the left-hand side, but what is more important, I think, is what you see on the right-hand side. That is the number of days above 0 degrees in the Arctic. So thawing temperatures in the Arctic. And as you can see, if you go one slide back, please. And as you can see on the slide, around 2000 it started to increase. So from having about a third of the year with temperatures above 0 degrees, we now have almost half of the year when the snow is melting. And that has tremendous effects for the Arctic. That has cascading effects throughout the ecosystems, including on human livelihoods. And for those of you who do not believe me, come to my hometown, try to cross the river on the ice in springtime, and you definitely understand that when you have water in its frozen form and water in its liquid form, it's two major different things, which has impacts. Next slide, please. Yeah. As I said, we've been running monitoring programs since the very beginning. That's where we started. And we do them panarctically. So we monitor, in this case, air quality throughout the Arctic. This shows some of the stations we have used in our monitoring of black carbon, for instance, including some of the stations in Russia, which are now not operative for us. Next slide, please. Okay. Yeah. And we have been working with short-lived climate pollutants since. Could you make it into presentation mode, please? And we've been working with short-lived climate pollutants since the very beginning. Since 2005. I hope we can get the slide up. And AMAP was also, and the Arctic Council was one of those organizations bringing forward black carbon to the international arena, leading to the establishment of CCAC and others. As we already in 2005, 2006 started working with them. And we've been frequently since then, been publishing reports on short-lived climate pollutants, including the 2021 report, which I'm going to refer to now. And I'm also going to talk a bit about the latest policy brief, which we published yesterday. Next slide, please. Next slide, please. Yeah. So why is short-lived climate pollutants important? Well, when we talk about short-lived climate pollutants, we talk about a range of compounds, but the most important one I'm going to talk about today is black carbon and methane. In particular, black carbon, it is important for two reasons. It has effects on human health, because black carbon is an important component of what we call particulate matter 2.5, really small particles, about a 20th of the size of your hair. And they have the feature that when you breathe them in, they will cross the barrier to your blood, and they will cross and they will accumulate in the body. And they're a major cause of pulmonary arterial diseases and death of pulmonary diseases, cardiovascular diseases, and so on. But also they're important climate enhancer, and one of the attributes to Arctic amplification. And the reason for that is particular black carbon is that it reduces the albedo, while
white surface can reflect about almost 85 to 90% of the energy from the sun. As soon as you remove snow, it reduces rapidly, and the sea surface, for instance, absorbed about 93% of the energy from the sun. Black carbon has the effect of taking away the surface albedo and to reduce the reflection of energy. And it has such a strong effect that one of the most famous explorers in Norway, Otto Sverdrup, when he tried to get out of the sea ice when he was stuck in 1904 and 1905, he first tried with dynamite, unsuccessful. The next year, he just spread the ash on the snow, and it took 2 weeks, and he could sail out. So that is the effect it has. Next slide, please. When it comes to health, just to understand the extent of the impact, if just in the Arctic states, if we just implemented the current legislation when it comes to emissions of black carbon and shorter climate forces, we could reduce premature deaths by 66,000 just in the Arctic states. And also, if we just implied the maximum feasible reduction we have, given the technologies we have today, we can almost reduce the premature deaths with 100,000 just in the Arctic states. Every year, annually, globally, it's about 7 million people dying of air pollution, and black carbon is a major component to that. Next slide, please. So, what are the sources for black carbon and methane emissions in the Arctic? Well, you see three of them here. Next slide, please. Next slide, please. Yeah. This graph shows on the upper side, it shows the Arctic states, while the lower slides show the observer countries to the Arctic Council, which is mainly some Asian states and European states. But what you can see when it comes to black carbon, which are the two circles on the left, there's a major difference in the contributions or the sources to black carbon from the Arctic states compared to the others. While the Arctic states, the main emission comes from surface transport, including shipping. For the other states, the main contribution comes from residential combustion. Likewise, when you speak about methane, the main contribution in the Arctic states come from the industry, while the main contribution from non-Arctic states come from agriculture. So that is also important to understand when you want to do regulation. Next slide, please. So what is the status of black carbon today? Well, black carbon has been highly debated when it comes to the impact on climate change. When you look at the IPCC's 5th assessment cycle and 6th assessment cycle, the importance of black carbon was reduced. That is due to we're measuring it another way. We've been analyzing that, and in the policy brief we released yesterday, we do say that even though the impact has been reduced due to the way we calculate it, it still is an important contribution to global warming. In particular in the Arctic, it's still a very important contributor to Arctic amplification. And therefore, global policies are warranted. And what I would say is most important here, you have to remember that when it comes to short-term climate pollutants, it is mainly benefits of reducing those, both when it comes to climate change, when it comes to health, and when it comes to technology and livelihoods. It's much easier to do that, and also when it comes to black carbon, it's a much quicker way to reduce the impact on global climate change than just on CO2 alone. So, thank you.
Thank you very much, Rolf, for the very good presentation. Now I'm gonna head the space to Sean Pryor. She's gonna join us remotely via Zoom. Are we ready with the presentation? No. It's Sean Pryor, and she's gonna join via Zoom. Dr. Sean Pryor is the lead advisor to the Clean Arctic Alliance, a coalition of 24 nonprofit organizations campaigning to protect the Arctic from the impacts of shipping. Sean specializes in interpreting marine science to support conservation and management policy and advocacy, and has over 30 years of experience of contributing to a variety of international, regional, and national marine management and conservation frameworks, including the International Maritime Organization. She has also taken secondments to government bodies. So now we're going to hear from Sean. Thank you, Sean. Sean, can you hear me?
Yes, we can.
Okay, it's your turn, please. If you could start, thank you. Thank you.
I'll go ahead then, thank you. Just sharing my slides. Can you hear me okay? Can everyone hear me okay?
Yes, we can hear you.
Excellent,
Thank you.
Thank you. And can you see the slides? More importantly, probably.
Yes, we can also see the slides.
Excellent, thank you. Hello everyone, I'm sorry that this has taken a little while to get sorted. I just quickly introduce the Clean Arctic Alliance, which is a coalition of 24 non-profit organisations based across the Arctic and focused on addressing the impact of shipping on the Arctic, and in particular emissions from ships of super pollutants, black carbon and methane. We focus on black carbon in particular because it is a short-lived climate forcer which has a disproportionate impact on the Arctic because of the effect on snow and ice, and as a consequence, habitats and wildlife, and on local communities. It has a 1,600 times greater impact than an equivalent amount of carbon dioxide on a 20-year global warming potential basis, and is responsible, along with ozone and methane, for nearly half of the global warming experienced to date. As sea ice retreats, access to resources in the Arctic is increasing, and shipping is increasing too. In the last decade, there has been around a third increase in the numbers of ships operating in the Arctic, and the distances being sailed have more than doubled. Inevitably, increasing shipping in the Arctic leads to increasing pollution, and regrettably, many of these emissions are totally unregulated, including discharges of scrubber wastewater, grey water, underwater noise, and black carbon. In 7 years, between 2015 and 2021, emissions of black carbon from ships operating in the Arctic more than doubled. And work that we will publish later this year will show that emissions are continuing to increase, and around 2,500 tonnes of black carbon were emitted by ships in 2024. Following the publication of the IPCC's 6th assessment report, a myth started circulating that black carbon emissions from ships was no longer considered a priority. There remains uncertainty about the radiative forcing estimates of black carbon, and this was used to question the effectiveness of regionally based, extensively studied and well-defined efforts to reduce black carbon. However, while the global warming potential of black carbon has been lowered, the warming potential of black carbon when it settles onto snow and ice was doubled as compared with the 5th assessment report, and black carbon warming on snow forcing is estimated to be between 2 and 4 times that of the equivalent carbon dioxide forcing. The impact of black carbon is recognised to be primarily a regional or local issue, especially when it is emitted in and near to the Arctic, and it is sources rather than emissions that are important. It is anticipated that the 7th assessment report cycle will better define the global black carbon impact, but important aspects are likely to remain the same: the regional importance on sources in and close to the Arctic, and the importance of addressing low-hanging fruit, such as maritime shipping. Another myth linked to emissions of particulate matter in particular and black carbon within that is the idea that allowing ships to continue to emit sulfur oxides or SOx and injecting sulfate and other chemicals into the atmosphere or spreading silicate beads onto the Arctic Ocean surface will contribute to cooling. Reducing black carbon emissions remains a high priority, not just for the climate, but also because of the clear and well-documented co-benefits for human health and for ecosystems. Oops. This map shows the black carbon emissions from shipping in the Arctic in 2021 and a number of different boundaries. And it's important to notice here that the most significant concentrations of black carbon emissions from ships in the Arctic are actually coming from outside of an area known as the Polar Code Arctic waters. In fact, 2/3 of emissions from ships in the Arctic come from outside of the Polar Code area. There is actually a very simple solution which would see black carbon emissions from ships reduce significantly. If all ships operating in the Arctic were to move away from heavy, dirty residual fuels to cleaner polar fuels, emissions of black carbon could be significantly reduced. Polar fuels would include distillate fuels, which are cleaner than the residual fuels traditionally used by larger ships and are in widespread use globally. These cleaner fuels are already used by many of the smaller ships operating in the Arctic, but not by the larger ships, primarily because they are around 15 to 20% more expensive than residual fuels. They can be characterized very easily based on their density and viscosity and other parameters. And there are now new fuels coming onto the maritime fuel market with comparable lower black carbon emissions. Hydrogen, methanol, ammonia could also be considered polar fuels. Moving away from oil-based fuels is essential, but all fossil fuels will ultimately need to be abandoned. And in attempts to reduce use of oil-based fuels and carbon dioxide emissions, some ships have moved to liquefied natural gas or LNG. LNG is basically methane, another super pollutant and dangerously potent greenhouse gas, which we will hear more about shortly. Clean Arctic Alliance is advocating that Arctic shipping moves to distillate fuels in the immediate short term, but also recognizes that while distillate fuels are readily available today, they too will eventually need to be phased out as the sector decarbonizes. A move away from residual fuels needs a new regulation to be agreed, and for this to happen, a country, and preferably an Arctic state or states, needs to submit a proposal. There is an opportunity coming up as early next year, the International Maritime Organization will discuss the concept of polar fuels further, and proposals for discussion must be submitted by early December. In addition to government action, we also need the shipping and fuel sector to support an immediate switch to cleaner distillate and other alternative fuels with low black carbon emissions. Thank you.
Thank you very much, Sean. Now I'm gonna hand over to the next speaker. I'm gonna be presenting, so I have two hats for this event. One of them is a moderator and as a speaker. My name is Nancy Garcia. I work with Equal Roots. It's an NGO based in Canada, but I'm actually based in Mexico, so I work remotely. And we work to make the shipping industry a more sustainable industry. And the topic of my presentation is LNG. Thank you. LNG in shipping and the triple planetary crisis. So I'm going to focus on methane. LNG is basically methane, and why methane fuels are not the answer. Next, please. LNG is a fossil fuel. Is if you if the actual name is liquefied natural gas. So the name of it might mislead us, but it's actually a fossil fuel, and it's methane based. Methane is a short-lived pollutant. It lasts 10 years in the atmosphere compared to CO2. No, can we go to back, please, to the other one? Yeah, thank you. So in this graph, you can see the life cycle of methane and compared to CO2. Next one, please. The first myth that we have to bust for LNG is that LNG plays a key role in decarbonization. In the shipping industry, or a lot of players in the shipping industry, see LNG fuel as a transition fuel because they believe it's cleaner, but that's actually that's a myth. It's not. LNG is an exacerbating global warming, has an exacerbating global warming potential. Methane is 87 times more potent than CO2 in over 20 years. And the global methane emissions are record high, and we can see it here in this graph. How were they very low in the 1990s, and they started climbing, and now we're very high. The next slide, please. The second myth is that LNG is a solution for fuels, heavy fuel oils. But actually, the tipping points mark an irreversible climate change, like the Arctic ice melt that has been already explained by James and by Rolf. And methane from LNG is a trigger in the Arctic, where rapid ice melts is underway, as our speakers before have already made that clear and explained into detail. And this is we can see the threshold. And the next slide, please. And James made this point very clear, and about the methane released by the melting ice. So as the glaciers are shrinking, they're exposing bubbling groundwater springs, and that they could provide what we consider now, we have underestimated as a greenhouse gas source. So this is just getting it's just getting worse. And the research suggests that these methane emissions will likely increase as the Arctic glaciers melt and more springs are exposed. The next slide, please. And the third myth is that LNG reduces shipping emissions. Again, this is seen as a transition fuel by the shipping industry, and they have mentioned that the methane slip, which is the methane that is released by ships while they are in transit using LNG, it's been reduced by the newest technology, by the newer ships designs or engine designs. But actually, we see that this is not true. The LNG fleet, which is in the black line, is slowly increasing. But if we look at the methane emissions that are the red dotted line, we see that they're increasing slightly more than the LNG fleet. So actually, we're having more methane emissions from fewer ships, for fewer LNG fleet. But still, the industry, some cruise companies and some large shipping companies are seeing it as a factor, as a transition fuel. Also because there's going to be in the next few years an oversupply of LNG in the world, because LNG is also expanding, is being more extracted, and is being more produced. So there's going to be an oversupply in the world, and they want to take advantage of that. The next slide, please. So LNG in the shipping in the the United States, Canada, Norway, and Russia have very big reserves of natural gas, and they are not moving away from them, so they keep exploiting them. And LNG as a fuel is also expanding, as I said before. For example, Norway has the largest fleet of ice-class LNG ships in the region, followed by Sweden and Finland. And also, Norway has LNG fueled-based fishing ships, vessels. And in Russia, LNG is used in ships and is restricted to export of oil and gas. And Russia is the second world largest natural gas producer, with approximately 83% of its natural gas coming from the Arctic territories. And gas extraction and processing of LNG and trade has grown, including import and export terminal in the Arctic nations. But this is a global phenomenon. It's not only limited to the Arctic. We see the largest natural gas producer, LNG producer and exporter is the U.S., and they're expanding its capacity. And now we've seen growth in Canada and also future developments also in Mexico. So it's just a market that is growing. The next slide, please. And so this shows the full cycle of LNG. So from the extraction and the processing to its transportation through pipelines, and then through gas, and then how it's liquefied in port or terminal development to fuel the ships in the port terminals. So the extraction process of LNG is related to oil and natural gas, and for this they use fracking or hydrological fracture to extract natural gas, and then it is transported through pipelines that they cross that are very long. There's going to be one in Mexico. It's going to be 800 kilometers long, and they also have leakages of methane on the way, and it also damages the lands and the territory, usually of indigenous peoples and populations that are vulnerable. And then it's brought to the coast, to port terminals, where the natural gas is liquefied through a process that it gets cooled to minus 162 degrees Celsius. And this process also requires a lot of energy and has a very high impact in the air quality of the facilities or the areas near the facilities. And then there has to be some kind of port development, because the LNG to be transported in ships. So LNG is usually transported. So we have the ships that transport LNG, and we also have the ships that use LNG. But to transport LNG, you need very large ports and facilities, and to develop that infrastructure already also requires a lot of impacts in the port, in the marine area, and this causes a lot of damages to the fisheries and the livelihoods of the people near there. So we can see that it's not only the part of LNG being used as a fuel, so what we call well to tank, but also the full life assessment, the full cycle assessment that needs to be done from the extraction point to its final users. Next slide, please. That's why we call to rethinking decarbonization, to a call for true solutions, that we keep an eye and do not forget the biodiversity impacts, of course the climate impacts, the pollution, but that we remember to think about it as a triple planetary crisis. Not only think about decarbonization, but think it holistically, so we can have an equitable and just transition. The next slide, please. And finally, we have the recommendations. Sean was talking about it before, so we call for the Arctic nations to require all the ships to urgently reduce emissions of CO2, black carbon, and methane by 2030, and move to alternative and non-fossil fuels and other forms of propulsion. and also that ships operating in the Arctic, this is a simple solution that change from heavy fuels to distillate fuels or cleaner non-fuels in order to cut emissions of short-lived pollutants. And we call for the shipping industry to focus on energy saving practices and technology. So this is kind of the operating side of the shipping industry to be able to reduce their fuel consumption. And then to call into the private and public sectors to stop investing in LNG infrastructure, because this will cause further delays for the sector transition and to true fuel solutions in the future. So this is related to what I was saying before. It's seen as a transition fuel, and also because there's a lot of the expansion of LNG is growing rapidly. There's going to be an oversupply, and the heavy users of LNG as a fuel are seeing it as a window of opportunity. So we're asking the private sector to rethink this, and also to the public sector, because also in the light of the advisory opinion of the International Court of Justice, the states have the obligation not to promote any more fossil fuel infrastructure to be able to achieve our climate goals. So this is something that needs to be taken into account by states, and there should be no delay on that. And thank you. So I'm gonna head it over to our next speaker. Our next speaker is gonna join us remotely too. His name is Sam Devin. He's from WWF Canada. See that? See?
Thank you very much. Can you confirm that you can see my slides?
Yes, Sam, let me just first introduce you very quickly, and then you can start. We see your slides and we can hear you very well. So Dr. Sam Devin works from WWF Canada as a lead specialist in conservation and shipping. He supports WWF Global Network as International Maritime Organization lead, and he's based in Ottawa. Thank you, Sam, for joining us remotely, and we look forward to hearing you.
Thank you very much, and hello, everyone. Global biodiversity is in crisis. According to WWF's 2024 Living Planet report, marine species populations have declined by 56% in the past 5 decades. This loss is driven by habitat degradation, overexploitation, the accelerating impacts of climate change, and chronic pollution. All industry sectors have a role to play in slowing and reversing biodiversity loss and climate change. In shipping, this means transitioning to cleaner fuels, managing existing sources of pollution, and preventing new forms of pollution. And that brings me to why I'm here today. Scrubbers, also known as exhaust gas cleaning systems, have emerged in the last decade as a major source of shipping pollution. They enable ships to meet sulfur emission limits while continuing to burn inexpensive residual fuels. This cuts operating costs while shifting the burden to the environment and to other ocean users, including coastal communities. Their use results in more climate emissions, lower air quality, and the qualitative transformation of air pollution into a new form of ocean pollution. So, in line with this session's theme, we aim to bust the myth that scrubbers are an acceptable equivalent to lower sulfur compliant fuels. The International Maritime Organization regulates air pollution through Annex 6 of the MARPOL Convention, which limits the sulfur content of marine fuels. Over the past 2 decades, the IMO has progressively tightened these limits to protect human health and to reduce the environmental and economic harms from sulfur dioxide and particulate emissions. The global cap is currently set at 0.5% and 0.1% in emission control areas. As an alternative to fuel-based compliance, Annex 6 allows administrations to approve equivalent technologies, provided they are at least as effective at reducing emissions and do not impair the environment, human health, property, or resources. Today, scrubbers are widely used as an alternative to lower sulfur fuels, but evidence shows that they do not meet the criteria of a true equivalent. Even though scrubbers can effectively reduce sulfur oxides when scrubbers are functional, ships equipped with scrubbers don't produce equivalent total emissions. First, ships with scrubbers emit more particulates than vessels using compliant fuels. Environment and Climate Change Canada finds that, in Canada, the scrubber-equipped fleet emits about 57% more PM 2.5 and more than 100% more black carbon. As we've just heard from Dr. Pryor, black carbon is a short-lived but powerful climate forcer. It's responsible for about 20% of shipping's total climate impact, and when it settles on snow and ice, it accelerates melting, resulting in the loss of essential habitat for Arctic species like polar bear, seals, walrus, caribou, and others. Second, scrubbers require energy to run, and so using them increases a ship's total energy demand. This means more fuel burn, and as a result, higher CO2 emissions. Higher particulate emissions mean more air pollution in port cities and coastal communities. Exposure to fine particulate matter contributes to heart and lung disease and increases the incidence of premature death. Canada's modeling shows that in the Canadian context, widespread scrubber use could add tens of millions of dollars in healthcare costs annually, as well as result in additional pollution-related deaths each year. These higher particulate emissions also undermine the role and purpose of emission control areas, which are designated in part to reduce particulate emissions near population centers. These areas do not set explicit particulate limits. Instead, their effectiveness depends on ships using lower sulfur fuels that naturally produce less particulate matter when burned. But the story doesn't end there. Scrubbers don't just pollute the air, they also pollute the ocean. They work by spraying engine and boiler exhaust gases prior to stack emission with a buffer solution, usually seawater, resulting in the production of contaminated waste that is then discharged into the sea. Scrubber wastewater is, in fact, the largest operational waste stream from ships by volume. To give an example, in Canada in 2022, where only about 1 in 20 ships was fitted with a scrubber, these systems produce nearly 200 billion liters of wastewater, including nearly 27 billion liters in marine protected areas. For context, that's nearly 50 times the combined volumes of sewage, grey water, and bilge water produced by all ships in Canada over the same period. And of course, it's not just about the volume of waste, but also what's in it. Scrubber wastewater contains high concentrations of persistent and bioaccumulative contaminants, like dissolved metals and polycyclic aromatic hydrocarbons. These pollutants can accumulate in the water column, in sediments, and enter food webs, where they can harm marine life even at low concentrations. Laboratory studies show us that seawater containing even 1 part per million scrubber wash water significantly reduces sea urchin reproduction, and exposure to 10 parts per million results in deformities in shellfish larvae. And at higher concentrations, zooplankton that are exposed to scrubber wastewater die within minutes, leading some researchers to conclude that scrubber wastewater is in fact more toxic to plankton than crude oil. This waste is also generally strongly acidic. Discharging into the ocean accelerates acidification, which in turn weakens corals and other calcifying species. And in enclosed or low alkalinity waters, high scrubber use can potentially cause annual pH declines equivalent to up to several decades of climate-driven acidification. In short, scrubbers can be described as pollution machines. They transform air pollution into water pollution while simultaneously releasing more climate pollutants. Scrubbers seemingly failed to meet the criteria for an equivalent under MARPOL Annex 6. They also appear inconsistent with obligations under the UN Convention on the Law of the Sea, including but not limited to the duties of states to protect and preserve the marine environment, to control pollution from technologies under national jurisdiction, and to avoid transforming one form of pollution into another. Fortunately, there's a very simple solution, and that is to ban scrubbers. Compliant lower sulfur fuel is widely available, and the majority of scrubbers at sea today have already paid for themselves, or if not, soon will. As a next step, countries should stop approving scrubbers on ships flying their flags and prohibit scrubber discharges within their jurisdictional waters, as Sweden, Finland, and Denmark have recently done with open-loop scrubber discharges. At the international level, governments should work through the International Maritime Organization to amend MARPOL Annex 6 to prohibit the use of scrubbers as an alternative to compliant fuels. The next opportunity for such a submission will be the IMO's Pollution Prevention and Response Subcommittee meeting in February 2026. This concludes my presentation. Thank you very much.
Thank you, Sam, for your presentation. Now I'm gonna pass it on to our last speaker, Roald Honders. He's head of climate action and clean air at the Marine Environment Division of the IMO. He oversees the IMO's regulatory work on energy efficiency and emission reduction of international maritime transport. Roald holds a law degree with specializations in international environmental and maritime law. Before joining the IMO, Mr. Honders held various positions in the European Commission.
Não está saindo.
Mr. Honders held various positions in the European Commission, the European Maritime Safety Agency, and in the port and the logistics sector. It's an honor to have you here.
Thank you very much, Nancy. Great pleasure to be here for this very timely, especially in this very hot environment, panel. And thank you also to Sean and to Sam for providing us already with quite a good overview of what IMO does in terms of regulatory work to reduce some of the pollutants and emissions that we've been discussing this afternoon. I'll try to keep it relatively short. Thank you very much for putting that forward. The IMO, I guess some of you here in the room are not that familiar yet with the IMO, but we are part of the UN system. So we are a specialized agency based in London that is actually mandated to regulate both the environmental performance from ships as well as the safety performance for ships. As we are a UN agency, we have a membership of 175 member states, and these members jointly have to come up with regulations that can control the emissions from shipping. And so it's not an easy process in order to get to consensus, but I think we have shown in the past, and Sam and Sean also highlighted some of the work that has been done in the past, we have been able to regulate a number of the atmospheric emissions from ships. We do that through binding regulations. So other than some of the other UN agencies, we do not or primarily work with convention requirements, MARPOL Annex 6, that entail binding regulations once they enter into force for ships operating worldwide. And in that way, we regulate the about 50,000 ships operating worldwide. Generally speaking, our regulations are goal-based, meaning that they are technology and fuel agnostic. So you won't see in our regulations a general advice, prohibition in relation to the use of certain fuels. So it's unlikely that you will hear the IMO saying that LNG cannot be used anymore. What we will do, though, and I'll come to that in a second, is of course regulate, in particular the life cycle emissions of all the fuels, all the alternative fuels that are available for the shipping industry, on a well-to-wake basis in order to allow for a fair comparison of their climate contribution. Now, when it comes to black carbon has been on the agenda of the IMO for quite a while. We haven't made as much progress as compared to some of the other pollutants in regulating. This is primarily due to still divergent views on how to best and how to most efficiently regulate black carbon emissions from the IMO perspective. noting that there's a lot of impact, or there's a lot of elements relating to the use of black carbons, notably kind of the engine requirements, how the engine is set, how the engine is maintained, but also what type of fuels are being used by the shipping industry and how these are burned in the engine and how it relates to black carbon emissions. Now, we have made some progress in the past years, particularly in relation to some of the voluntary measures. So there has been an agreement on a resolution, particularly on protecting the Arctic from shipping black carbon emissions, which includes a recommendation on the use of distillate fuels in the Arctic. Last year, a new resolution was adopted containing guidance on best practice on recommendatory goal-based control measures to reduce black carbon emissions in the Arctic. And there's a whole range of kind of measures that ship owners, operators can take in order to reduce their black carbon emissions, varying from technology options and other kinds of control measures that can be taken by ships. Work is ongoing, in particular to developing further emission measurement, monitoring and reporting campaigns for black carbon. But more importantly, as Sean already mentioned as well, we have had some discussions about a specific polar fuel standard in the last meetings that took place in London. And that actually has gained quite a bit of traction in the last meetings. And we invited member states, observer organizations to submit specific proposals, regulatory proposals, including amendments to MARPOL Annex 6, on how to introduce in the regulatory framework this concept of polar fuels. And I think you probably are aware that some progress has been made in kind of the Nordic Council on the concept of polar fuels. And so we expect that some of these conclusions and recommendations on the polar fuel concept will find its way now to the IMO. Next slide, thank you. More importantly, as a framework that the IMO has in place in order to regulate greenhouse gas emissions, in 2023 a strategy was adopted by member states, which was adopted unanimously, to come to net zero emissions by 2050 from global shipping. Since then, since 2023, member states have been working on regulations, binding regulations to control greenhouse gas emissions from shipping, and it's very clear that these regulations do not only focus on CO2 but on all greenhouse gas emissions. And we actually, member states developed a so-called IMO net zero framework, which comprises a comprehensive set of a global fuel standard together with an economic pricing mechanism for ship emissions. Now, you may have probably heard that during the last meeting, which took place in October in London, the discussions on the adoption of these regulations were adjourned for a year because of divergent views amongst member states. So we will use this period now in order to identify how we can find broader consensus amongst the member states in order to get these measures, the IMO Net Zero framework, adopted next year. There is continued work also on other pollutants, including methane and nitrous oxide. There is a so-called working group looking into, particularly into the, and that's kind of the onboard measurements for methane and nitrous oxide emissions. And that work has already developed some draft regulations that will have to be discussed in the upcoming sessions, including new regulations on a so-called fuel certification framework, so where the IMO can look into some of the upstream certification of emissions, emission factors, including for LNG. We have received various proposals from member states on proposals for emission factors, both for the upstream, so the production part, as well as the part of emissions on board of the ship, so related to the engines. And so together with the ongoing work on binding regulations, we hope to put in place kind of a robust framework that looks into the entire life cycle emissions of all the shipping fuels available. Now, LNG is one of those, but there's work also ongoing on ammonia, on hydrogen, and again looking into what are the entire well-to-wake or the life cycle emissions of these fuels. Lastly, and I think Sam referred to this already as well in his presentation. Can you do the next slide, please? Recent progress has been made on the designation of additional emission control areas for nitrogen oxides, sulfur emission oxides, and particulate matter. And so within the IMO, there's a mechanism whereby member states can identify specific areas that have stricter requirements in terms of sulfur emissions and nitrogen oxide emissions. And the Northwest Atlantic, so including the Canada area, is one of these proposed areas, and we are waiting for the next session of the Marine Environment Protection Committee in April to adopt these amendments so that they can enter into force in 2028, allowing or actually prescribing lower sulfur emissions used in these areas. The Norwegian Arctic Sea, or the Norwegian Atlantic coast that you can see in red on the slide, together with the North American and the Canadian emission control area, have already been designated as low sulfur emission areas, and these requirements will enter into force in March 2026. So this is where I'll stop. I think we have had a long list of presentations. Just to repeat what both Sean and Sam said, that the next juncture of discussions will be in February. And we're looking forward to receive proposals both on polar fuels, but also on scrubbers and the further regulation of discharge water from scrubbers. So thank you very much, Nancy. Back to you.
Thank you very much. Now we're gonna open a short round of questions from the audience. Do you wanna ask? No? If you feel, we can do it in Spanish too, for those of you who speak Spanish. I can translate. If there aren't any questions from the audience, I think we can wrap it up. It's been really hot. Thank you for everyone that bear with us, and thank you for to all the speakers for being here, and to the organizers, Pam and Amy. Thank you for all the logistics and for the invitation. Thank you. Have a good day.
Thank you, everyone.
Thank you.
Thank you. I have to go.